All right.
Yeah.
Hello, everyone, and welcome to the second and final technical session for the Spring 24 cohort hosted by Amuye. We are an ed startup dedicated to equipping young adults and university students with the skills needed for data-centric careers in today's dynamic job markets. Through hands-on internships, we provide a realistic environment, combining specialized coursework, informative webinars, and practical projects. Today's session is a great example of the industry-relevant projects presentations we offer. Thank you for joining us. My name is Mercy, and my job is to make sure that you have a great experience at Amoye. I'm joining you from Ibadan, Nigeria, and will be your host for today's session. I'd like to welcome to this event everyone present, our incredible interns in the current cohort. Kudos to you for making it this far. Thanks to the Amoye Fellows and the Amoye team who have made this session possible. We are psyched to announce today that we have with us Dimeji Mudele. Dimeji Mudele is a postdoctoral fellow at the Harvard T.H. Chan School of Public Health. He obtained a B Engine honorary one in electrical and electronics engineering from the Federal University of Technology, Akure, Nigeria, and also holds an MSc in electronic engineering, summa cum laude. Oladimeji has a PhD in electronic computer science and electrical engineering, 2021, from the University of Pavia, Italy. His work centers on the application of geospatial information and data science methods for connecting climate and health outcomes with policy. He was a beneficiary of the Marie Sklodowska-Curie Actions and the German Academy Exchange Service scholarships. Between 2018 and 2019, he was a visiting scholar at the Argentinian Commission for Space Activities and the Institute of Computing of the Federal University of Alagoas, Brazil. In 2019, he received the Premio de Laurea Award as the top international scholar in University of Pavia. As an employee at Voiced, he co-built a text-to-speech technology engine using deep learning-based methods, including convolutional neural networks, transformers, recurrent neural networks, self-supervised learning, adversarial learning, among others. And today, he will be speaking about the topic time series modeling for air pollution monitoring with a focus on correcting low-cost PM 2.5 sensor measurements. We know that that sounds different from what we had previously advertised. However, our speaker has decided to graciously share with us a tool he has developed, hence the fortunate topic change. Also, before I hand over to Dimeji, please carefully take note of the following. Feel free to post your questions and comments on slido.com using the event code 1612268. Again, the event code 1612268, and they will be promptly attended to. A Google form has just been opened to collate attendance for the interns. Use the secret code prompt, all lowercase, and the form link is going to be sent both on YouTube and on Zoom right away. And the form is only going to be opened for 10 minutes so that you can focus on the presentation. Dimeji, over to you. Thank you very much.
All right, so let's get it let's get going. I think we have folks already online. Let me see. Oh, we have 70 something folks. So what first of all, I would before getting into a presentation, I would just want to share some of the things that I have been up to. Like folks know on the call, like okay, I don't know if people know, but the introduction already gave a bit of what I do. Um, so some of what I do is around, machine learning, image processing, and then recently also then looking at how machine learning overlaps with how machine learning and satellite image processing overlap with public health applications, especially looking at building early warning systems for vector-borne disease or climate response functions for disease exposure among population. So that's some of the work I do. So for you to be able to do that kind of work, some of the most important things you need to do is around data development, helping standardize and develop databases that help to do that kind of work, or developing tools that enable other people to do those kinds of work much more easily. I don't know if are there people on this call who has any particular interest whatsoever in specifically image processing. If you could signify in the chat. I just want to get an idea of the sense of what, people are thinking, where you see in your career going based on what you're learning and all that. I mean, or let's do it like this. What are your specific interests in data science, in AI, in machine learning? Like, do you have specific areas you're looking to take your career towards? What domain are you looking to focus on? Could you, if you could, just just use the chat and just say something in the chats. Anyone? Yeah, just mention in the chat, say, oh, you know what, I'm interested in public health, I'm interested in large language modeling, I'm interested in, I don't know, environmental science. Someone said, I would love to focus on the agricultural sector. This is actually someone said finance. Nice. So in agricultural sector, in fact, I have some work also going on where we're looking at using satellite imagery to estimate crop yield in some African countries. And then based on the estimated crop yields, we want to then look at what is the impact of changing crop yield over time on, things like malnutrition, and how can government then intervene in that process? You understand? So that one is there. Someone says spatial analysis for agriculture and hydrology. Oh, that's good. Agriculture and hydrology, spatial analysis. Oh, good, good. So agriculture and hydrology, um, if you want to do agricultural work specifically, um, if you want to do agricultural work specifically, you need to also be thinking about doing things like vector data processing, satellite image processing, right? Someone said climate modeling. Oh, that's wonderful. So climate modeling also is something I am beginning to get into. I have a collaborator who works in that area that I need to learn more from. But a lot of climate modeling work is very interesting. Medical AI. Mm. So I have a friend who works in cancer genomics, who has a data science background. So you can go from data science into even the guys at the medical school here at Harvard. But his background is in, stats and data science, but now he's in cancer genomics. So that's a very, very interesting area too. Yeah, the good thing about people sharing their areas of interest in the chat like this would mean that other people who are still deciding might also see what other folks are trying to do and then use that to decide their own. Finance. Hmm. So finance is a very big one also, especially for folks who want to work on Wall Street, do like, asset value prediction, real estate, insurance. Insurance is a very big one also, underwriting insurance, a lot of machine learning applications in that field. So yeah, so I'm seeing some very interesting cybersecurity, that's fine. Biomedical informatics. So I see that a lot of people here actually renewable energy mix. I see that a lot of people here actually might need some satellite image processing skills, right? Because satellite imagery is very important in things like environmental sustainability. Someone said in areas like healthcare, in areas like agriculture, um, green energy, right? Finance, yeah, a little bit in insurance because people use satellite imagery to, for example, do disaster management. Let's say there is some disaster happening somewhere and buildings that are supposed to be insured have been destroyed. Then you use satellite imagery to see what is pre and post event um what does pre and post event look like in those areas, and then use that to then estimate how much the insurance company would have to pay. You understand? So those are very important. Okay, cool, cool, cool. That said, okay, there are applications, and there are applications in telecommunications, of course. A friend of mine did some research around using satellite imagery to optimize deployment of telecommunication masts. So where should they be placed within a city to ensure that we minimize the cost of deployment in terms of how many masts should we deploy, and we maximize coverage, you understand, across the whole place. So those are very important. So yeah, so I would encourage that, once you're done with this first phase of your training, you try to find, you know, projects that help you to then, dive in. Yeah, digital twin. Yeah, digital twin is something that people are talking about recently. It's getting a lot of traction. People are raising money even doing digital twin work, but it's still very early, right? The good thing about doing something this early is that if you truly do it and you know it, then you get opportunities quickly. But the challenge with doing it is that there's not enough resources yet, right? So you would have to figure things out on your own. There's not enough experts around who can teach you stuff. But then the good thing is if you cannot figure it out, then you get opportunities very fast. Because I mean there are very few people who know it. Drug discovery is also very, very good actually. I like this one. I like drug discovery because it's also there's a company I was almost collaborating with at some point in Germany who it's a very big company actually. They do drug discovery. Yeah. So picking all of those things out, I think that among Python and R, which language do folks think is most applicable? If you do Python, you do R, just signify, just say Python. If you do both, you can say Python and R. If you do Python, say Python. If you do R, say R. Let's say because there are advantages of both, and the conversations around it is always, oh, you know what, people think Python is superior to R, but it depends on the field you're working in, the area you're in. Oh, Python, there's a lot of Python people here. So many people here want to be in the industry. Ruby is good um, for building very resilient applications. But if you want to do your experimentation on machine learning experimentation, I'm not convinced that there's enough tools to support um, experimentation in Ruby. But it's a very good language for like building resilient applications. Anyway, so yeah, so there's a lot of Python people here. So one of the ways you can hack the process of becoming an expert in whatever field you choose to work in, one of the ways you can hack the process of becoming an expert, and it's something that has worked for me very well, is to contribute to open source. You understand? So you find projects that are aligned with your area of interest, right? You find projects that are aligned with your area of interest, and you try to use those projects or try to contribute to those projects on GitHub. You go on GitHub and then you keep track of projects that are aligned with your area of interest. If someone said cancer genomics, no, or what did someone say? Use drug discovery. So you can find tools that are doing drug discovery, for example, Python library on GitHub that is a drug discovery tool. Then you find something to contribute. It might even be documentation. You might just find an error in the documentation or in the README, and you just add it, and then you do a pull request and they actually merge your pull request. If it's a large project, then you become a contributor to that large project, and then you put it on your resume that you're one of the contributors to this project that is as large as this. How do you claim that it's large? Oh, people are using it for science. A lot of publications have used this tool, and I am part of the contributors to it. That essentially cements you in a different level in the field. So I mean, I just thought that it's very useful to quickly share some of this very, very few things. So talking of open source, so do you all have what's it called? Do you all have GitHub profile? Do you have a GitHub account? If you have a GitHub account, let me share one of the things I have been up to recently, especially for some of you who are doing climate modeling work, for example. So this should be relevant. You understand? You can start it and just to keep track so that you can remember, so that all the developments that are coming up, you can see them when they are developing. So this is one of my projects. You could just check it out and start it. It's in the chat. Someone said macroeconomics. That's a different field entirely. Anyway, so yeah, good. So yeah, I actually recently started to do some work in econometrics, causal inference. It's a field in data science. I would write the name in the chats. So I dropped the GitHub project I'm working on chat also. So causal inference is a field in data science where you're trying to infer causality from data. You understand? And a lot of econometrics, if there are folks here who studied economics in school, like you've done some econometrics, fixed effects models or random effects or all those kind of models, difference in difference, all those kind of models are used, but they're not mostly taught in data science courses. You don't find them, especially in common data science methods. You find them, like, which is just machine learning prediction, prediction, prediction. This is a different mindset completely. You understand? So I would encourage that you can also check it out. All right. Yeah. So yeah, so that said, let's see what else is then productive to get into. So I want to just do a presentation also on, yeah, so yeah, thank you very much. Let me see if there's anything anyone else is saying again. So what have we said so far? We've spoken about areas where you can work in data science, right? We've spoken about how do you establish yourself in those areas. You get one of the ways to establish. In fact, maybe this is what I should have spoken about in this whole chat, in this whole talk, but I just come into what I need to talk about eventually. But I think what we are talking about is very, very important. A lot of people have data science skills, but they actually don't know how to channel it. Where is the biggest place to put it right now? In fact, what I tell people is this: large language modeling, the people that are going to do large language modeling and be successful at it, right? They are already doing it now. You get it's a very, very crowded area already, too crowded, right? And it requires too much resources for you to be able to compete. You need to have all those very, very big GPUs, such that you have to, if you don't have them, then you can't compete because you're not able to develop the kind of models that would bring you to the forefront of the field. So you want to look at other areas where people are not applying data science methods yet, or maybe people are applying it, but you can also compete if without needing to spend a lot of money to buy a very big machine, right? And I love the fact that people have diverse, like environmental sustainability is a very big area now. Climate, climate change is happening, especially if you're based out of India, based out of Nigeria or Africa. I see that there's a bunch of people out of Nigeria here and out of India here. If you are based out of those parts of the world, those are the problems that are pressing right now. There's flooding, there is extreme weather events. How do you use machine learning and data science to address these issues? If you do some work in that area right now, you can get opportunities faster because there's a lot of funding in those areas you get. So you need to be strategic in how you position yourself in the field. Don't just be a data scientist broadly. Try to find an area a niche area where you then develop your expertise in that would take you to the forefront of the field very quickly. You get. So yeah, biomedical informatics is also very, very, very interesting, especially if you're doing deep learning for pattern recognition and things like imaging, medical imaging, for example. It's a very big field, right? But that is also very resource intensive. You need a lot of money to be able to get the kind of data that makes you competitive. If you are working with open source data that's available online to everyone, that is not the most competitive work you want to do. Most of the competitive work you want to do you have to be able to work with some very niche, very niche and very niche data that, you probably develop the data yourself or you access it through your relationship or the resources around your institution. So then, yeah, oil and gas is also very good. Robotics is very good, right? Especially if you come from an engineering background, because it's very tough if you don't. So yeah, thank you. So let me just quickly get into, since there are people on this, so there's Gen AI. What about Gen AI? So generative AI is an umbrella term for many things you get. Um, Large language models are generative AIs in a sense, you understand, right? So you can't just be a Gen AI person. You have to be a Gen AI for what exactly? You can do there's video generation, there's image generation, there is text generation, right? So you then focus, and then in Gen AI, there are many methods of doing generative AI, um, variational network encoders, or token prediction, like what you do for ChatGPT. Yeah, essentially, right? So you need to focus, you need to find an area to focus in, and then but Gen AI is very interesting. It's a buzz term now. People just use it and throw it around, but you need to filter down to what exactly you're going to be doing. What are you, what, I mean, what I tell people to do also is don't focus too much on the methodologies. Like, oh, Gen AI, this one. Find a problem. You understand? Find a problem, right? Focus on finding a problem first. That is important, that has a lot of attention on the world, and then try to solve that problem. You might need Gen AI to solve that problem, you might not. You understand? Right? And then if you solve an important problem, you communicate the solution that you have provided either through a publication or through some press release, then people get attention to you, and then you can put that in your resume, and then it moves your own career forward. Rather than just getting engulfed in all these new terms coming up every day, and then you're always drowned and you're not making any progress. You understand? Oh, okay. Yeah, that still comes under some industrial application of AI and ML, which is predictive maintenance for machine reliability. So yeah, there's a lot of industrial application of AI and ML in all these companies. Yeah, yeah, so that's interesting for sure. That's very interesting for sure. So yeah, business analyst, yes, that's good. Someone spoke about finance, right? So you say business analysis, the question would be what kind of business, right? Okay, I mean, if you already know the companies you would rather work with as a business analyst, right? So what I tell people is if you are going to be a business analyst, you want to ask yourself, business, what kind of business? So if you already know the kind of businesses you want to work with, go and find out the kinds of problems they have and then work on those kind of problems and then frame your resume around that so that you can, when you present it to them, they can see and say, immediately realize that, wow, this guy is valuable to us. He's already solving the problems that we have even without joining us. So that you're not just going around downloading Titanic data online and then predicting how many people died. Like those things are not useful for anybody. You understand? There's no company in the world that's trying to predict Titanic. So yeah, essentially. So you need to find actual problems that it relates to what companies are doing. Let's take, for example, you want to work in a logistics company that does food delivery around a city. Let's pick one town in the world, Paris. You understand? So then, and you like that company, you want to work there. You're thinking of sending an application to them, or maybe you want to reach out to one of the recruiters in the company via LinkedIn. So one of the things you could do is you find a very interesting project in logistics, right? Probably solve, and then try to solve that using some data science method, and then communicate it and try to see how you can shape the communication of it to ensure that it goes into how their business can improve just because of what you did. You get. And that way you actually do something that is useful in the real world, not some random data science. Yeah, because what is happening these days is people just go and do one or two or three random data science stuff online and put it on their resume, and so just avoid that bandwagon. So yeah, that's true. So what I'm going to present today, for example, is a real world application of data science, right? Let me just quickly share my screen to show that. Yeah, let me see. I have a lot of tabs open. It's just intense. Let me see. Okay. Let me see. I see. Awesome. So yeah, let's get into. So what I want to talk about is that so one of the issues you have if you live in India, if you live in Nigeria, one of the issues you have to grapple with is air pollution. Air pollution is actually a problem because of industrial wastes, because of things like industrial waste, things like transportation, things like human activities, agriculture, deforestation, a lot of anthropogenic effects actually drive pollution in the atmosphere. But this pollution rather in the atmosphere is not inconsequential. It is actually very consequential, especially to the health of human beings. And one of the most important pollutants that you actually find in the atmosphere that comes from human activities is what we call the um, particulate matter. You understand? So the particulate matter is actually there is particulate matter 2.5, there's particulate matter 10, which the 2.5 and 10 just relates to the size of the pollutants in the atmosphere. The danger of PM 2.5, which is particulate matter 2.5, is that it's so small that it can get into it can even get into your blood. And it's responsible. I mean, studies have shown one of our papers was published yesterday, for example, shows the differential effect of mortality, right, across different zip codes in the US, right? As a result of PM 2.5 in the atmosphere. You understand? So we use a neural network to actually estimate that, right? And so even in the US, where there is relatively cleaner air, right, compared to like the global south, there is a lot of effect of PM 2.5 in the atmosphere, right? Um, it could lead to things like asthma, chronic obstructive pulmonary diseases, cardiovascular diseases, stroke, like cardiovascular diseases like stroke and the likes, and actually has mortality effect also, right? And some of the things that cause it especially is, burning of coal, wildfire. There's a lot of forest fires recently, in Europe, for example, and then in the US and California, forest fires in the summer every year, right? In Canada, there was forest fires last year. Like it was really, really intense, right? Power plants, um, yeah, so the point is that knowing this to be the case, we need to be able to estimate the amount of pollution we have in the atmosphere in every environment, because if you cannot solve, or you cannot manage a problem you cannot measure. And this is the idea of data science. Data science is, collecting data on things that are of interest to us, and then looking at how we can analyze those data to get insights that we can feed back into, policy or, business decisions, right? So now, in the US, so the particular project I'm going to talk to you about is going to be focused on the US, right? And in the US, the air quality measurements are done by what we call the US EPA, which is the Environmental Protection Agency, right? And they use very expensive equipment to do that. For you to get very precise measurements of air quality, you need to use this high quality, what we call the the reference grade monitors, right? But the problem with those is they are too expensive. You can't have them everywhere. It's too much. It's tens of thousands of dollars. So what you now do is to augment the network that you have. You now support um you now support um those very sparsely positioned reference grid monitors with low cost sensors. But the problem with low cost sensors is that they are not very accurate, right? But you can have as many of them as possible. In fact, I think they cost about $300, right? The ones that are used in the US cost about $300. The ones that we used recently in Africa, in Madagascar, right, it cost about, let's say, $170. So you can literally, for just the cost of a single reference grid monitor, you can get a lot of low cost sensors, right? But the question is, what is the accuracy of what you're measuring? So the main idea is this, is that if we use a low cost sensor rather than a reference monitor, what are we losing? We're losing performance. How can we compensate for that? We can use data science methods to compensate for that by doing what we call statistical correction. You understand? Statistical correction is essentially saying that um, while I place my low-cost sensors around, right, I will place some of those low-cost sensors just right next to reference grid monitors, right? So when the reference grid monitor is measuring, the low-cost sensor is also measuring in those same locations. So I have measurements from those two, and I can use for example, just a regression, right, to map one to the other one and then correct it, right, essentially. So that's the main idea. So I mean, so it's a model. You have Y. Y is your reference grid measurement. Um, YR is your reference grid measurement, and then YI is your low cost sensor. And then X is all the other covariates that you need to compensate for, like temperature, because your low cost sensor measures things like temperature, humidity, and then you also need to control for things like distance to road, since you know that road traffic is actually a contributor to pollution, right? So distance to road and a couple other things around you get that you use as your background covariates. Now, that said, I'm coming. What's wrong with my? Okay, so this project was done in Denver, um, Colorado, in the United States, and it involved a project. It's a real life, real world project. In fact, it's one of my colleagues who was working on this, and then I worked on certain parts of it also. Um, and the idea was just to improve the air quality in schools in Denver. If you're listening to me now, you're in Nigeria, you're in India, this is an interesting project. You can prototype it, write a grant, get funded, you understand, and try to make air quality better in your city. If you just with, I think if you get $5,000 of funding from all this global, foundations, agencies, you could go a long way. You could get as much as 20, 30 local sensors, put them in your area and do analysis of them. And those kinds of things. Those kind of things have more power on your resume than working on Titanic data set. For sure, 100%. You understand? Right? Because it shows a lot more things. It shows that you have initiative, you have leadership, you can come up with a project, raise money for it, deliver the project, things like that. So now, um, so yeah, so let's just get into um the main part of it. So what is the story? The story is that you have deployed reference, you have low cost sensors deployed out there in the wild, but you know that their readings are not correct, so you want to correct them. How do you correct them? You use regression analysis, right? To map from your low cost to your reference grade. And that way, you're able to spend less money by buying low cost sensors because you can correct their readings using statistical analysis. So yeah, so I want to quickly get back to, so it's instead of just doing all this, getting into code, let's not waste time. So what do you think if you have this kind of model where you have reference grade measurement of air quality? So let me give you an idea of what these numbers look like. Why R air can be, let's say, 10, and then why I air can be 12. So that means that the low cost sensor is overestimating the pollutant level by 2. You understand? And then X is just all values of background covariates. You understand? So what kind of, if you're doing a regression analysis and you're fitting this in a linear regression, what kind of error metric would you use for this, for example? Can anybody just reply in the chat? Like, how would you evaluate this kind of model? Okay, someone said RMSE. That's one. MSE, okay. Okay, there's mean absolute error. Okay, someone said recall. Mm. So recall, you can't use recall for this one. Um, Someone said RMSE, someone said MAE. So now I want to ask you very, very simple questions. What is the difference between using MAE and RMSE? What's the difference? What's the difference between using MAE and RMSE? So that you're not just having all of this things in your mind, you need to be able to think about them intuitively. What do they measure? What do they differently measure? Like, in what situation would you use MAE? In what situation would you use RMSE? And can so those are very good metrics that you have come up with now. MSC, yes, MSC and RMSC is more sensitive to outliers. Okay. And then MAE is not more sensitive to outliers. That's correct. That's correct. Uzodima. Yeah, that's correct. That's a very good one. You could use MAE when you don't take outliers into consideration. RMSC penalizes outliers. Yes, that's correct. That's correct. Thank you. Thank you. Thank you. Taiwo Akisoya. Thanks. So now, yeah, that's correct. Um, so in terms of penalizing outliers, can you think very deeply about how does it yeah, MSC and RMSC, they penalize outliers, that's true. How does it penalize outliers differently? Okay, let me just share this one. It's difficult to ask this question. So if your outcome variable, a lot of times people do this standardization. If your outcome variable is between 0 and 1, you can normalize, right? If your outcome variable is between 0 and 1, it's actually the opposite. If you think about it, the square of a number that is less than 1, right? So you could use your calculator right now, right, and check to see what is the square of 0.01. Okay, let someone just drop this for me. What is the square of 0.01? What's the square of 0.01? Exactly. So you see that the square of a number that is less than 1 is less than that number itself, right? So in fact, you are only penalizing, right? Your penalization only happens when y is greater than or equal to, right, 1, if you understand that. Because in fact, when y is not, when y is greater than or equal to 1, let's say y is 2 now, right? So 2 square is 4. So you enlarge that error, you understand, right? You enlarge very large errors. If you now have an error of, let's say, 20 times 20 becomes like a very large number, right? 200 times 2 is 400. You understand? Okay. But when you are between 0 and 1, if you normalize y, the opposite is what is happening. In fact, MAE gives you larger penalization for large errors than RMSE. Do you think that does that click in your mind now? Does anybody understand anything? You get. So that thing that you described there is not always true. You get. It's true on the scale of the outcome variable that you're measuring. So you have to think about the outcome variable. What is the range of my value? That's why you should do like this distribution plots when you're doing your EDA, exploratory data analysis. You like distribution of your values. But whenever you normalize, all of these things are not true anymore, right? But you can denormalize and then do your your loss or your error computation for this to be specifically true. So yeah, that's correct. So thank you. I don't want us to just get into this talking where we're just talking and then showing code. I want us to like be very, very. So let's look at this again. For example, so given this model, so you have YR and YI. I've only been getting responses from two people, Uzodima and Taiwo. So this time around, and there are 90 people on this call. Come on. So this time around, we are going to have to flip it. Anyway, so if you know that so looking at this model again, right? So you have YI and YR. Yeah, and then you check for the rest of the background covariance you want to control for. If you think about this very well, um, and you want to fit this model, right? What are variations of this model you would fit? For example, one variation of the model is just to not even control for X, just YI and YR, and then you fit it like that. You understand, right? What else could you do again? What else could you do? How would you do model selection for this? Does anybody know how to do model selection for this? How would you do model selection? Like, for example, you want to drop variables that are redundant, or you want to check for multicollinearity in your variable. How would you do that? Yeah, feature importance. Oh, that's yeah, you can do feature importance, or you can just even use your statistical test. Like which statistical test? That's a good question. That's a good point. Yeah, you can check for correlation between features. So that's a good. That's we're having a decent conversation. T-test, one way and over. Okay, chi-square test. What would you do to use the chi-square test to check? What exactly are you checking when you're using chi-square test? What are you checking? Awesome. Nice, nice. So I see. Nice. Okay. Let me just bring my screen. So I think it's for category of variables. Okay. All right. So let's just leave all of this. Let's leave all of this. So that in reality, so I think I think people folks get it now. You get it. So let me see other questions I can ask. So yeah, cross validation. So I want to set the stage for this one. So cross validation is like very important. So you have your training. So you're collecting training data. You have training data in 3 locations. You have test data in 2 locations. You understand? How would you? So first of all, what is do you know what cross validation is? What is cross validation, and how would you describe it? Can anybody just mention something about cross validation that you know? And then we will now get into this. How would you do cross validation for this specific application where you're collecting low cost sensor information in 5 locations? You understand? But then you're collecting this data over time. You have time series, what we call multi-site time series. You understand? Yeah. Okay. It's a way to pick. It's not a way to pick an optimal algorithm, right? Cross-validation is a way to is a way to remove bias in evaluation of a model. You understand? A way to remove bias and overfitting in evaluation of a model, right? So how would you do cross-validation for the situation where there are 5 locations with multi-site time series? You understand? How would you, and then let's say you pick 3 locations for training and then you test over 2 locations. How then would you do cross-validation after that? Yeah. So yeah, Olubola said you divide the data into subsets. That's a good point. That's correct. Exactly. You understand. So you divide your data into subsets and then you train on one, you validate on the other one, right? And then you go again, you redivide it again, you understand. So let's say in this case, for example, look at my screen now that I shared. You find that there are three locations: the National Jewish Hospital, La Casa, and I-25 Globeville. Those are three locations you train on, right? Then you test on these two locations that are down here, right? Now, your next model that you want to fit, right? You will now train on NJH, La Casa, and this one down here. And then you test on another two. So it's called leave location out cross validation. You can leave one location out. Some people do leave one location out cross validation, or you leave two locations out cross validation. You just change the locations that you're leaving out and then using for test every single time. You understand? So you have to think about cross validation for the kind of application you're doing. If you're doing time series, for example, people do forward chaining where you train on one time and then you test on the next time in front, and then you just keep doing that chaining. So there are many ways, but you need to read about these things very well. But when you're reading about them, don't cram, don't say, okay, cross validation, just put it in your head. No, try to understand why. Why are we doing this thing and what does it help us achieve? So when you read it in that way and you understand it in that way, you don't have to even remember it. You just, whenever you are trying to apply it, you can come up with a variation of it in your mind at that moment that fits your own problem. You understand? So that's the best way to approach data science. You're not just cramming things in your mind, you're understanding the reason why these things are being done. So that way you don't need to even do them the way they have been described. You can do your own as long as you can create an argument that that supports why you're doing it the way you're doing it. I mean, this is actual education. So yeah, let me see again what else is useful to communicate here. So exactly, so that being said, now I will share with you the link to the code for this. That you can go through the code at your free time, right? You can go through the code at your free time so that you can just see how some of these things have been implemented. The slides will also be shared with Messi so that everyone can have the slides. So yeah, I don't want to get into like just looking at code. So what if you have any questions, you can drop your questions on the chat now. And also don't forget, because there are big updates coming up on this, my big updates coming up on this my package that I'm developing for processing NASA satellite imagery. It's gotten a lot of acceptance in the community recently. Lots of emails from everywhere. So yeah, so you could just start to get to, so that for those who are interested in staying on track with learning image processing, for example, if you start it, you find out about what is happening on the project, and then you can reach out to me if you want to contribute in any way, and I mean it helps your resume. I mean, a lot of folks who are working on it recently, one of the things that they even get to be able to do is, you know, put it on their resume or apply to grad school, ask me for recommendation letter based on the work they did on it and all that. So yeah, assuming I have a large data set of like 10,000 or 100,000, do I necessarily have to do cross validation? Hmm, that's a good point. Yes, you do. Yes, you do have to. You still do have to. The problem is how do you do sampling in a way that is unbiased? Because when you're doing cross validation, you are literally just sampling. You're sampling and saying, out of this 100,000, I would take out 20% of them. So the argument for cross validation is that I want to show and prove that the result I got is not just for a specific segment of 20% that I use for testing, that it generalizes to the whole data set. You understand? So you can do bootstrap sampling, and then you can do 1,000. For example, if you have 100,000 samples, you can do up to 1,000 sampling. So cross validation does not even have to be, getting the subsets. You can do bootstrap sampling where you run a single analysis, you bootstrap sample a hundred thousand samples from your data set with replacements. So you can even have multiple versions of the same sample in the data set. You run your analysis again, you see what the error is, you do it again, you can do it over 1,000 times. I do a lot of reviews recently. I do a lot of reviews for journals. And one of the things I check if I see your table results and you have error estimates or precision recall, and there are no confidence intervals for what you are. It's gonna your paper is gonna get rejected. For me, it's a deal breaker. I mean, because you don't know, there's no way to tell that what you are presenting is generalizable in any way. So it doesn't matter the amount. You need to cross validate. You need to get confidence intervals. You understand? Um, because your error is most of the time not a single value. It's a distribution of values. So you want to see how does that change? If I change my sampling of the data set, how does my error change? And you want to do that many, many times. All right. So what is the next question? Anybody, any question again, so that we can quickly. Yeah. All right. Thank you very much. Do we have any more questions very quickly? It's already running towards 9 o'clock or 10 o'clock my time. Okay. So there are no such questions, I guess.
Hi,
Yeah.
good afternoon.
Oh, good afternoon. Yeah.
Yeah, sorry, I can't type fast, and my question is going to be a very long question. So I just decided let me just use mouth to just say it. Okay, so I was thinking because when you were saying cross validation on this time series data,
Mm-hmm.
this approach which on the screen now is a very good approach. Actually, I didn't. The initial thought of cross validation was to gather all the data and then of course skip one part
Yeah.
like that, do that iterate
Iteratively. I see.
and that. So but printing a kind of a this thing out, a center out, and then training, what are the pros, what are
Okay. What are
than just gathering all the data together?
Yeah, it's not a question I can fully answer you right now because you would need to do a lot of thinking about this to get to intuition level. But the point is that if you want to leave some of the data sets out and then train on some of the data set, the question is which one do you leave out? Which one do you train? It is not the same for every problem. It has to go towards what problem are you trying to solve. That's why I was trying to encourage you initially that you should start from a problem. Otherwise, you're just doing with a blank mind, just working on the data sets. I think Titanic or whatever. It's an abstract problem. There is no real concrete idea around it. So if you think about this one, what are we trying to achieve? Let's think about it for a moment. What we are trying to achieve is that we want to have a model that generalizes to new locations, such that if I install another sensor tomorrow, I can use that model to correct that sensor. You understand? So if my idea is to generalize to new locations, it means that I want my model to be able to predict very well and be robust in new locations. So I leave locations out. I split on locations rather than splitting on data in time. You understand? If my idea is that, oh, you know what? I want to be able to forecast my data, my model is focusing on how, if based on current or past data sets, I need to predict the future. Then I leave future data sets out, right? And I predict on past. That's what we call forward chaining. Let's say I have data set from January to December every day on stocks, right? And I want a model that is able to predict forward. You understand, right? So my cross validation will now be okay. I take January, February, I predict on March, I get the error. I take January, February, March, I predict on April, I get the error. I take February, March, April, I predict on them. Then I do test on May. I get the error. So, because that is what fits into that problem. You understand? The model is focused on future prediction. If my idea is to generalize to new locations, I need to think about constructing a cross validation that is for that purpose specifically. You understand? So that's the point. Can it help models to perform better, or is it just getting errors in? It's not, yeah, it's not helping your model to perform better. It's helping your evaluation to be better. You understand? The model performs whatever it performs. Yeah. You said?
Hi. Hello, can you hear me?
Yeah, I can hear you.
Okay, I just need to confirm if you are done with your slide because I have some questions that are coming in from YouTube on my end.
Okay. Okay. Yeah, please go on. Thanks. I'm done.
All right. Okay. From Adeleke. Hold on, let me read it. So the question is, if I train a data and the accuracy result is over 0.9,
Okay.
should I be concerned about overfitting or cross-validation? But before you answer, please let me just make a brief announcement. The second form is going to be dropping this to the audience. So we're going to drop the second form and the code. So you do well to fill that in. The secret code is network, all in lowercase. Yeah, so I'll be dropping that. And yeah, you just fill the form. It's just going to expire in the next 5 minutes. I can go on to answer the question, Jumoje.
Yeah, yeah. What's the question again? If it's
Okay,
0.5,
let me take it.
should I, if
Yeah,
it's
let me take it
0.9, should I be
again.
concerned about cross-validation and overfitting? It depends.
Let me
I mean,
take it again.
yeah, go over it again. Thank
If
you.
if I train a data and the accuracy result is over 0.9, should I be concerned about overfitting or cross-validation?
Maybe, no, your concern about overfitting and cross-validation has nothing to do with the your error or your accuracy and your model. You understand? So let's say, for example, let me help you frame this. Overfitting is very simple. Overfitting means that the performance on training data is way more than what you get on test data sets. So let's say you train a model and then you predict on your training data set, you get 0.9, right? And then you run it on the test data set, it gets you 0.6 or 0.5. That is a case of overfitting. You understand? Right? That is a case of overfitting. It means that you overfit on the training data set. In fact, that's the idea of overfitting. Overfit on what? On the training data set, right? You are cramming, you cram the training data set in such a way that when you now see new data, you're not able to do well with it, right? So that's the idea of things like regularization or cross-validation, right? Which is, in a sense, rather than overfitting on a training data set, you vary the training data set a lot, and then you have more pool of tests to test on, and then you look at what is the standard deviation of that, or what is the confidence interval. A confidence interval you can already just construct by looking at the second and the third quartile of your error and see what is the range of it. If your error ranges too widely, let's say, for example, or your accuracy range is too widely, accuracy, let's say the lowest accuracy you get after doing your cross validation is you at 0.4, the highest accuracy is 0.9, then that already tells you that this model is, you understand, it's just on vibes. You understand? I mean, it depends on the test data that you choose. You could go to 0.4 or you go to 0.9. So that's what you're trying to see. You get. So when you say overfitting, if you get 0.9, the question is on what? If you get it on the training data set, okay, now then you have to do it on the test. If you do it on the test and you get 0.9, and then you now cross-validate, and then you get, your cross-validation error is between 0.88 and 0.92, then that's fine. You understand? Next.
All right, thank you for that. We have another one from Uzodima. Can cross-validation fix data leakage issues?
So data leakage issues is, as far as I know, no, right? It is your design, it is your experiment design that fixes data leakage issues. You understand? One of the ways you can have data leakage, for example, is when you're doing standardization and normalization of your data. If you normalize your training and your test data together, let's say, for example, you need to do like this, you remove the mean and you divide by standard deviation, that's standardization, right? So if you're doing that, if the mean that you use and standard deviation you use includes your test sets, right? So you have already leaked some information from the test set into the training data set. Right? So when you're doing your design, you ensure that you conduct things in such a way that there is no leakage. It is not cross-validation that helps you to achieve that. It is the design of your study that helps you to achieve that. Yeah, he said what of 0.9 what?
Yeah, I can hear you. Okay, you want to go on with the one in the chat?
No, someone asked what of 0.9 on training and 0.8 on testing. It's not a numbers thing. Don't put this thing in your mind that okay, this number, when I have this number, it is overfitting. No. Think of overfitting as a deviation from the training accuracy to test accuracy. You understand, right? If you have 0.9 in training and 0.8 in tests, right? So what you want to do is you want to try to see, can I improve on this? Can I reduce the gap, or can I improve this by moving from 0.8 to, if I've already used regularizers. I've used regularizers. I have done what else again would you do you have done cross validation, you understand? I've used regularizers. Yeah, then this is what you get. That's fine. You get. And then the question you want to ask yourself again is, what are other people getting? Other people that have worked on the same problem using the same data, what are they getting? If it fits into that frame, then you're fine. And you're like, okay, yeah, it's not a problem. You get. So don't just think of it as, oh, you know what, 0.8 and 0.9, okay, so if it's, no, it might not be. You get. It might not be. Yeah. If you check and you find out that other people are using that same data set and they're getting much closer, you understand, like let's say 0.9 in training, 0.89 in test, then maybe your own case might then be overfitting. Then you try and see how you can push it forward, something like that. Yeah. So let's take one more question. I have to like run after this.
All right, I have one question here. This person is, how can different error measurement techniques be used to effectively assess the performance of various models?
Yeah, there are different errors. Like you can check your R square. You can check let's for example, you can use correlation to check if I'm predicting stocks. Let's say somebody said finance in the beginning. If I'm predicting stocks, right? Or predicting the markets, some markets variable. So you can use correlation coefficient to just check if what I'm predicting matches the trend of what is the true value. I'm not at this point, I don't care about if it matches the actual value or if you are close enough in terms of, distance, right? So let's say, for example, if the true value has four data samples, which is 1, 2, 3, 4. If I predict 10, 11, 12, 13, that could be perfect correlation, you understand? So that assesses trend, right? But if I now use um mean absolute error to check, you understand, you will see that the mean absolute error is 10, essentially, because you have 10, 10, 10, 10 divided by 4. You understand, right? So you can assess now. So you see that if you use those kind of different metrics, it helps you to see that, oh, you know what, I am getting the trend, but my prediction is off by, a magnitude of about 10. You get. So you don't depend on what you are looking for. If what you are looking for is you want to know the direction of the market, is it going up or down? Then the mean absolute error value, you don't really care, because I mean it could go up by by 20. If it could go up by 100, but you don't care. You just want to know, is it going up? You understand? Then you can use correlation. So these things are going into what we call study design, designing your study to fit a goal that you have in mind. What are you trying to achieve? What is important? What is the problem you're trying to solve? Then you have a metric. The idea of the error metric is to help you assess, is my model achieving the goal I am trying to achieve? You understand? So you come up with an error metric that specifically takes you towards that direction. Yep. So that's it.
All right, thanks. Thank you, Dimitri, for that. All right, so I will just go on with the closing remark. So as today's webinar comes to an end, we officially wrap it up. Thank you so much, Dimitri, for sharing your insights and thoughts so generously. Every second we've spent here has been super informative. To our awesome interns and everyone who joined, I'm sure you've picked up some really useful tips and know-how from today's talk. Special thanks to the Hamway hardworking team and everyone who pitched in to make this webinar a success. Have an awesome weekend. Until next time, take care.
Okay, bye.
Bye, everyone.